Welcome along, ladies and gentlemen, to your weekly SETI Institute talks. We have today joining us Aaron Zent, who has come across to us from NASA Ames. And Aaron got his bachelor's in Earth and Planetary Science from Washington University in St. Louis, and then moved across to sunnier climes in Hawaii for his PhD work with Fraser Fennell, where he was working on the interaction of Mars's surface, subsurface, and the atmosphere. That's a theme that he has carried with him through his career. When he graduated from Hawaii, he came across to Northern California in NASA Ames, and for a while was working at the SETI Institute. Aaron has worked on several space missions, including Deep Space 2 and the successful Phoenix follow-up, where he was a member of the Mecha and Tiga teams. And today, Aaron is going to talk to us about a subject a little bit closer to home, only a little bit though. He's going to talk to us about unfrozen water in the Antarctic and implications for life on Mars. So if you'll all join me in welcoming Aaron.
Thank you. No, somebody actually went back and looked up my Vita. I have never looked at that since it was written. So yeah, I wanted to take a little bit of time and sort of discuss some of the things. New is really not the word for this. These are still sort of in progress pieces of work that relate. They have in common the role of unfrozen water. And let me get to the point here. Why do we care about this stuff? Well, the really juicy question is, could Mars' high latitude permafrost, where there's ice in the ground all the way around the high latitudes, could that be habitable, a habitable environment? Now, ground ice on Earth certainly is. Ground ice on Earth is packed with psychrophiles, and they thrive very happily there. These are rate of growth curves for three different major types of microbes. Everybody you know and love is in that bell curve, but the psychrophiles tend to do better at a little bit below the freezing point, and then we're not going to worry about thermophiles today. But you know, actual metabolism and growth has been measured in these things in ice down to minus 15 C, and they have survived and recovered from temperatures at the base of the Antarctic. The Vostok drill cores is 230 Kelvin, minus 40, something like that, centigrade. And you know, the people who have been looking at this have sort of come to the conclusion they're really not aware of what the lower limit of temperature might be just for survival and the ability to come back to life. And you know, life has always surprised us here on Earth. Ever since Viking, it seems to be getting, you know, the harder you look, the more you find of it. It seems to be more and more robust. So, and I actually wanted to just show the one of the places in ice that microbes tend to inhabit are these little triple junctions between ice grains, and within those junctions you tend to get layers of eutectic brine, where all of the dissolved salts and things get squozed out of the ice. They pile up in here, and this is electrofluorescence from a block of ice from 3.5 kilometers down in the Vostok ice core. Stuff has been underground a very, very, very long time, and there are still microbes in there doing just fine. And you got to think at temperatures like 230, I just want to sort of clarify, you're not really talking so much about microbes swimming around in teeny tiny pools. Microbes are typically on the scale of a micron or two. These films of water, the surrounding water surrounding them, is on the scale of several nanometers. So they're not swimming, they're just damp. But that is enough, that water provides enough mobility for them to exchange nutrients and waste products with the environment. Once they actually get it in and out of the cell, then it can diffuse away into the environment. But those very thin nanometer scale films on micron scale organisms is enough to feed them and keep them watered. But it does depend on that unfrozen water. Water is an unsatisfactory term. It seems like unfrozen water should be water. But there are actually a couple of different kinds of this unfrozen water. And by unfrozen water, here's what we mean. It's not a bulk liquid. It doesn't have the molecular structure of bulk liquid. It occurs always below 0 degrees centigrade, but it's not ice. These are interfacial thin films of H2O molecules that are kind of sensing the potential of the surfaces that they're moving around. They are mobile at some scale, and they come from a couple of different sources here, particularly in the Mars-like environment. So the first of them on the top here is physical adsorption. That is, anytime you've got a surface of any sort that is exposed to water vapor in the gas phase, water, because it is got a permanent dipole, it's kind of a sticky molecule. It tends to stick to those grains, pile up there, and the higher the humidity, the thicker those adsorbed films are. And they get thick enough, they start to get mobile. When they're very, very thin, the few molecules that are there tend to get stuck on really good adsorption sites, and they don't move anymore. So that's one source. Another source, particularly in ground ice, is this phenomenon known as pre-melting. And pre-melting basically is another one of these nanometer scale liquid-like films that tends to cover, as far as I know, and I'm a geologist, I bang rocks together for a living, so I've got to read some physics journals to find this stuff out. It seems to cover basically every crystalline material, in the upper 10% of temperature range before its melting point. Basically, you begin to get the first couple of layers, and it's kind of cleverly illustrated here with these little red squiggly atoms at the interface between two crystals. You get these mobile atoms. They're just not bound very well. Now, I said it occurs in every crystalline material. It only occurs on ice at Mars-like temperatures in any significant way, because that's the only thing, the only solid with a melting temperature low enough. And the reason that it shows up, the reason that this happens, is that it tends to minimize the free energy of the interface. The free energy of the grain plus liquid and liquid plus ice is less than the free energy of the grain and ice would be together. And so you've always got a little bit of this stuff here. So these pre-melted films, they get thicker and more mobile as the temperature approaches the melting point. And as I said, the adsorbed films get thicker as the atmosphere approaches saturation. So these things are sort of varying across each other. Okay, so that is unfrozen water. What's dry permafrost? Dry permafrost is just that. It's the non-cohesive, ice-free, totally free of condensed phase dirt that is permanently below the melting point. And this is a picture of that we took of the trench called Snow White from Phoenix. And what you're looking at there basically is ground ice. That is just plain old, that's a pile of dirt in which all of the available pores have been filled up with ice that's been cold trapped out of the atmosphere. And it looks like dirt. You actually can't glance at that and tell that it's ice. And then this stuff above it that comprises the walls of this trench, that's the dry permafrost. That stuff is pretty much non-cohesive, and it's, scoops up, but it is very, very cold. And usually, and by usually I mean in the two cases that are known, there's an abrupt transition here between this dry stuff and the patterned ground. And interestingly, there are only two places that this has ever been found. One is high latitudes on Mars, and the other is some of the McMurdo dry valleys in Antarctica. And so, as part of getting ready for the Phoenix mission, we actually went to Antarctica because we had these cool instruments, and why not? NASA had it. 2007, 2008 was the International Polar Year, so NASA put a pot of money on the table to encourage people to go do some work in Antarctica. And because we had the Phoenix mission coming up, we proposed to take some of our Phoenix stuff down there, and we wanted to do a little survey. In general, so here's Antarctica. The little black box is the big picture here, and the shore, where all the water is out here. And you get these valleys that are actually cut off from the polar plateau just by topographic highs. The ice can't flow over the rock and get down into these valleys. Snowfall is pretty limited, and so these things tend to remain bare, dry, and exposed. The primary source of water is snow, and it comes basically from the ocean, usually. And so what happens is, also as you go from high up in the valleys towards the polar plateau down to the shore, of course you're going downhill. So there's a gradient here. As you go from the polar plateau down to the shore, you go down to the subxerus, these dry valley areas very near the shore called subxerus, which is a three-syllable word meaning wet. And as you go to further inland to higher altitudes, you get into the ultraxerus domains, which is a four-syllable word meaning dry. And these ultraxerus domains are kind of this is the place where the dry permafrost occurs. So I want to focus a little bit on what we were doing and sort of at the latter half of our field work there. And where we were is a little place called University Valley here. There's a red dot you probably can't see. But you go, it's about 75 miles from the coast, and it's about a 1,500 meter elevation. It's this little, this is a picture of the whole thing. It's like 1 kilometer by 3 kilometers, a hanging valley that drops off into another hanging valley. And we were specifically interested in it because it shows this evidence of dry permafrost. There's a permanent snowfield up here. It seems to be mostly, the polar plateau is right up there. The polar ice is right there. And so there seems to be a sort of a permanent snowfield up there. And as you move down valley from that, there's ground ice that appears. It gets deeper and deeper as you move down valley, and eventually it intersects the surface of that snowfield. Excuse me. But between the surface and that ground ice is this dry permafrost. And there is a picture of the dry permafrost here. So, I should have mentioned this earlier. So what does ultraxerus mean? Ultraxerus is, it's a place, it's a climate type defined for the dry valleys in which the air temperature never really gets above freezing. So you can't melt in bulk very much. Most of the snow that falls here or that blows on here sublimates away again. It never turns to water. Salts, particularly things that are very, very soluble, will just accumulate in the soil. And these soils in very, very dry environments tend to grow because nothing is washing them out. And in particular, really soluble salts will accumulate in these things. And also, as I said, there's this kind of characteristic, interesting, permanently dry zone because you can't really melt the water. You can at the surface just get the surface to about 273. So you can melt a tiny bit there, and it may be able to infiltrate a few centimeters, but it can't get very far. And the ice table is down at 30-some centimeters depth. So And this is temperature data from a pit that is similar to and within a spitting distance of what I'm going to talk about here. Very limited melting, and basically at a macroscopic scale, you'd expect permanently dry stack of dirt.
Question, what is the relative humidity?
Well, it depends. During the, well, it's funny you should ask. No, never mind. I'll come back to that in a second. But it's typically around 50%. It goes down to 20 and up to 100% at times. So the bottom line is that there's the melting isotherm temperature data at 10 centimeters for January. It was the warmest month of the year there. The 0 degree isotherm never gets down as deep as 10 centimeters. You could, of course, get water through the soil column if you just kept pouring it in because it carries latent heat, but it would take an awful lot of that to do it. And so we are pretty convinced that this soil in the macroscopic sense has been dry for a really long time. And here's why that's interesting. First of all, there's really, in a lot of the evidence that we were able to look at and measure and characterize, there really isn't there is no evidence of drainage of the soil. It hasn't been washed. This is a profile of the leachable ions from that pit. 0 down to the ice table is about 34 centimeters. And in particular, this bright blue line, that's nitrate. Nitrates are just amazingly soluble. They tend to be carried away. You have a trickle of water going through there, and nitrates will be carried away, as will perchlorates, which we also found in this pit. Also, we found very, very little clay in here. There's really no evidence of water. But all the way down at the very bottom of this pit, where the temperature has presumably been, not been, any closer than 10 degrees centigrade to melting, two things. First of all, it's hard to see in this little brown line, but the population of live microbes at the base of the soil just about doubles from what it is over the top. I mean, there's at the very surface where, as I explained, you could get trace amounts of melting and a tiny bit of infiltration. You can see this big population up here, but it drops very quickly. And it's very low throughout the soil column until you get right down to the bottom, and then it starts creeping up again. And another thing that we found down there is crystals of what's called allochthonous gypsum. And allochthonous means it formed where you found it. And the reason we know that is because it's so pretty. This thing has not, nature doesn't transport things carefully. Grains that get moved around by the wind after they are formed, they get beat up in a big hurry. Saltation, all these things, these grains look like a mess. This thing is really very pretty. We only found a tiny bit of evidence of this, and there's no other. This remains a puzzle, actually, as to how you could actually get those things down there. Interestingly, the microbes that we saw down here at the base of in fact, all the way through the soil, these are heterotrophs. These are things that eat other things. They aren't primary producers that take CO2 and sunlight and produce their own organic molecules and structure. These things eat the bugs that lived above them. And so there is, in fact, in University Valley, there it is right there. There are primary producers here. And is it going to stop now? There we go. What they are is they're cryptoendoliths that live in these sandstone walls and photosynthesize. The sand in those sandstone walls is clear enough that you can get enough sunlight in there, and it acts as a little greenhouse. So there are these little, and you can see them in cross-section, little green organisms living inside that sandstone. Those are actually the only primary producers locally. And so ultimately anything that's getting eaten up is getting made by those guys up on the walls. And then down at the base of the soil column, they're being recycled again. So then we wanted to think about this a little bit, and instead of looking at data, which is really messy and confusing, we decided to put together a little numerical model of what we were looking at so that we know, it's prettier, it's easier to see. So we measured we had these temperature measurements, we knew where we were, we knew the thermal properties of the soil, so we can put together pretty easily, excuse me, a model of what the temperature is. And you can see basically in this particular case, version of the model, the melting isotherm does just get down to 10 centimeters, but still there's large scale space below it where it is always colder than freezing. So the other issue here with respect particularly to with the microbes is what's called the activity of water, and that's a measure of activity, and it is usually measured as the pressure, the relative humidity of water in the atmosphere relative to liquid water. And what that means is that below freezing, the activity of water is always less than 1. And when it's above freezing and you got liquid water sitting around, that's an activity of unity. And so there are a couple of different environments you might see in this valley in the summertime. And we wanted to take a look at both of these things. One of them is, what if you actually have condensed phase water, either liquid or ice, all the way through the soil from the top to the bottom. You might get that, for example, if you had a big snowstorm and then the sun came out and you actually melted, and that water would have the chance to infiltrate. It wouldn't get very far before it froze, but you could still, for a while, you'd have liquid or ice all the way through that soil. And so that's kind of this upper surface here. And what I'm plotting is the activity of water goes from up and down. There's the time of day. So you see the sun at this particular latitude. The surface temperature gets highest late in the afternoon. That has to do with the valley that we're in. And there's the depth. And you can see that this is 1. And at the ice table, it's down to about 0.87. Now, I'll tell you about this other one first. The other case, the case that comes after this one, is eventually the snow melts. It doesn't snow there much during the summer. Eventually the snow melts, the humidity in the atmosphere goes down to 20 to 30%, and you lose all that condensed water, all that liquid or ice that's in your soil, and what you end up with then is just vapor. Okay, and this is what the scene evolves to at the bottom, where now the activity of water is very, very low near the surface, but it still gets pegged by this ice at the same temperature. The temperature of the ice hasn't changed. It's pretty much constant at about minus 14 centigrade all through the summer. And so as you go from the surface to depth, you actually get to higher and higher activities of water. And here's the thing about the activity of water that is important for this particular discussion, is that there seems to be a limit, a metabolic limit, where the activity of water is kind of measured from 0 to 1. Has got to be at least 0.6 or greater for organisms to be able to use it. It's really, I'm not a biologist, I don't understand it, they tell me that's true, I believe them. But so you can see that what we actually did here on this graph is to use this pink contour to show where and when that condition applies. And the top surface kind of covers it, but you can see that as you go to greater depth in the late summer, the activity of water goes up and up and up, and eventually down here at about 25 centimeters, maybe a little bit deeper, you cross the magic line. And this seems to be, in general, the effect that is giving us this little oases of relatively high humidity but cold air down at the ice table and where organisms are living here. And they're doing it in these little layers of unfrozen water. Now, a couple of caveats here. At the scale of microbes, this calculation is kind of ham-handed. Things you can do much, much better than this at a very, very small scale and get much more favorable conditions. Another is it's totally unknown to me whether nanometer scale films of water could eventually precipitate or recrystallize or somehow beautify crystals of gypsum that are 1,000 times their thickness. This crystal is very big compared to the films of water that we're talking about here. So it's very skeptical that this is actually the explanation for the crystals, although it seems like it's a nice one for the microbes. Okay, so that's part of the equation, and I want to turn to Mars. This was one of the things. This is the reason we went to Antarctica, was so that we could exercise the Phoenix equipment, and then subsequently later that year we actually landed on Mars. And one of the really interesting things and unexpected things that we saw is this picture right here. You recall the picture I showed you earlier where there was ground ice that we scraped up, and it looked like dirt in the ground. That looks like ice. That is much, much purer ice than the stuff we were seeing in the other picture. And here's the key thing about this is that you can't get pure ice underground just by sucking water vapor down. There are only two ways to do this. Either you drop it out of the sky as precipitation and then you pile the dirt on top of it and trap it that way, or you do what's called in situ segregation. That is, the ice separates itself from the dirt and makes two discrete phases, two discrete layers, strata, big enough for you to see. And the way in which that process happens is through these very same thin films of water that are responsible for the feeding and watering of psychrophiles. These little thin films of water can do a lot of stuff if there's nothing else happening and you have a very long time. And so the general notion, the thing that we were keen to see, is that the existence of segregated pure ice in the subsurface could really tell us a lot about the habitability of Martian ground ice. And so we set about asking ourselves, could in fact you get ice lenses at the Phoenix landing site, or do we have to come up with some other explanation? Now, I want to start over here. Actually, the other explanation that some people hang on to is that this is precipitation. It's a snowbank that's gotten buried recently, and that's why it still looks pristine like that. The problem is it's stratigraphically, the ice is down here. This is the very first scoop that would eventually unearth that pure ice. It's down here. And on top of that ice is all of this dirt, and on top of that dirt are these great big rocks that were not put there by the wind. These things are the size of your fist. There's absolutely nothing that we understand about anything about Mars' geologic history that is going to move those rocks from far away to here recently. It's much more likely that, in fact, somehow the water went into the ground and then it segregated itself into discrete ice forms. So here's the way this works on Earth. And you see it a lot in cold, wintry places that we don't want to go to. And it works like, this is the usual story for the planet Earth. When you have water-saturated ground, and it begins to get cold. And the freezing front, this freezing line, starts moving down into the ground. Okay? And as it does, behind it, water gets converted from liquid to ice. And that leaves kind of a gradient of liquid water, which actually sucks water upwards through the soil surfaces, where it freezes out at these pure lenses of ice. And I'll get into a little more detail of that in a minute, but I first want to point out the problem with this from Mars is the word melting. It does not, and has not for millions and millions of years at least, gotten anywhere near melting at this site. And in fact, those ice lenses couldn't be left over from millions and millions of years ago. The planet's orbit is just too dynamic for that. So the question is, how key is this melting process? And for those of you who are not, science geeks, I apologize for what I'm about to do, but this is a good way to understand it, and it is an introduction to the model that I'm going to show you the results of in a minute. The relevant understanding how this frost heave and this ice lens formation works, you got to understand the basic forces that are taking place. And you can do that most simply with this process. It's called regulation. Regulation is if you've got a particle of something inert, like soil or a ball bearing, and it's sitting in a block of ice, and the block of ice has a warm end and a cold end, that particle will move through the ice to the warm end. And here's how it happens. There are three different things going on here in terms of forces. There is this pre-melting thing, this thermomolecular force. And what this really is, as I said, the molecules tend to orient themselves between the substrate and the ice out here in order to exert a standoff pressure. It keeps the grain and the ice from ever coming into contact. And the thinner that layer gets, the stronger the force is. It's because nature does not want to bring the ice and the rock together. It would much rather have a couple of layers of water molecule in there standing them off. Okay, so that's one thing. The layer is also thicker when it's warmer. So if it's warm up here and cold here, the layer is a little thicker at one end than the other. Now what happens is you've got gravity pulling down on the thing, and if it's actually moving, this water has got to flow through this tiny little layer back over to the cold side of the particle where it recondenses. And so it's constantly melting ice up here, freezing ice down here, moving the unfrozen water, that liquid layer around the particle, and after a certain amount of time, you end up moving the particle through the ice. And it's fast enough to see, to measure in the lab. Okay, so now to talk about these ice lenses, I want to first point out there's a distinction here, which only exists in a mathematical world. There's a distinction between initiating an ice lens and then actually growing it later. And I'll tell you what I mean, but it'll become clear, hopefully, what I mean by that. So we're able to figure out, there's a pretty good model for how you initiate an ice lens. And basically, all of those forces I just showed you are kind of balanced instead of a single particle in a block of ice. These are now balanced by particles just sitting on top of each other. It's the interparticle pressure. That stacks up and nothing moves. So in this freezing soil, this thermomolecular force and the gravity are balanced by particles sitting on top of each other. And once again, you've got the freezing front. It is moving down into the ground. And at some point, this is 273 Kelvin is 0 centigrade. That's nominally the point at which pure water freezes. Because you got a lot of curved surfaces and solutes in here, the actual ice doesn't start showing up until you're at a colder temperature, a little bit higher and colder than the melting temperature. And at that point, ice begins to form. And the colder you get, it's warm here and cold here, it's freezing at night, that's what happens. The colder you get, the more ice there is, as you see, in the pores. It takes up more and more of the pores. And that squeezes those little layers of water harder and harder. And if they are connected enough, what you can do, if you can do this sort of mathematically, is you add up those forces and you can figure out what the pressure at any depth in the ground, you can figure out how much pressure the grains are exerting on the ones below them. And as you change the amount of ice and water in here, the other forces get bigger and bigger, and eventually what happens is the particles unload. They just pop off, they float off each other, because now their weight and everything above them is being borne by the forces in these tiny films of water. And that's the key thing that we're looking for, is if you take a Mars-like environment, Mars-like soil, if you run it through the, what you expect, what do you get? And so that's just this little physical thing, this mechanistic model. To make it run for Mars, you got to put in, you got to know what the soil's like. So you got to put in some numbers for the soil, and then you have to put in some numbers for the environment. Now we're talking about looking over millions of years here. So what do we do about the environment? We kind of understood for a long time that there's a general rule. We know that the obliquity, eccentricity, and perihelion of Mars orbit all vary. They each have their own little characteristic frequencies. But that in terms of water and the atmosphere and in the ground, the thing that's really important is the obliquity, this tilt between the axis, spin axis, and the ecliptic. And at high obliquity, when the planet is tilted way over and the poles point more closely at the sun, remember we're looking at the Phoenix site, which is very near the North Pole. North Pole is where all the water is sitting. So when you tip the planet over and you're pointing all of that at the sun's higher, longer, the summers are warmer, the caps get warmer, the humidity goes up, it becomes much warmer and a much wetter environment. When the obliquity tilts back down, the caps get much colder, the Phoenix site gets much colder, the humidity gets much lower. And so that little dynamic between the caps and the ground temperature drive the ice table. And if you know where the ice table is, you pretty much know what its temperature is. And you need to be able to predict that for to do the analysis we're doing here. So, we can find this. This is a plot over 10 million years of just the obliquity. This is how quickly this thing oscillates. This is a prediction that you get of how deep the ground is. This is the current time here. That's 10 million years ago. And you can see at about 5 million years there's this break where this obliquity gets smaller, and all of a sudden the ground ice is ice is not restricted to being near the surface anymore. It spends a lot of time with much greater depths of soil being totally desiccated. Those are not interesting times for us. So we showed up 5 million years too late for the really fun stuff. And then I think I'm going to skip the discussion of how we do that. So the point is that you can if you make some assumptions about how the cap works, and you assume that the way it works now, the regolith temperature works now is the way it's always worked, you can actually figure out how deep the ice has been for the last 10 million years with high frequency, and you can figure out how warm the ice has gotten. And this is just a color bar calculation that shows, as you go from the present back into the past, how you spend more and more time above these threshold temperatures. And the blue is -15 centigrade, the green is -10, red is 0, that's the melting point. So you can melt ground ice in some of these instances is what this model predicts. So we did this, come up with a bunch of, kind of a look back through space and time at where and when you might expect to get the kind of relatively warm or wet or near melting conditions that we'd expect. Now, we did this in a couple of ways. As I said, the prediction's really sensitive to polar cap history. One thing that can happen is that when the planet tilts way, way over, the polar cap itself becomes unstable, and all the ice goes and sits on the equator. That's the coldest place on the planet. And when you do that, the situation changes drastically in terms of these growing seasons and really nice periods of warm, squishy, yummy ice. That gray stuff is the ghost of what it was the last time. If you let the polar caps all disappear at a really high obliquity, you lose virtually all of that. So there's a lot of sensitivity here. And there are a couple of things that you need to do to define the soil. And suffice it to say for right now, there's a bunch of soils that have been characterized, or libraries of these soils. And we don't have Mars soil exactly, but you probably don't need it. We have things that are probably close enough. The two things you really need to know is, as you cool off, how much of the pore space gets filled up with ice. That's how much ice, as a function of freezing. And then later, we'll worry about whether or not these lenses grow. And this is a permeability. This is how much water can flow through the soil when it's full of ice, when it's freezing. So here's this model, just to check this process. And we went back to a point 4 million years ago where that model had predicted that you'd actually melt the ground ice. Because this is the way it works on Earth. So you want to see it work in the same way on Mars. And what we have here is all of these go time from noon to midnight in the middle and noon again the next day. And God, I can't read any, I'm standing here. Yeah, so what you can see here is that you actually get, this is temperature. Right there is the 0 degrees centigrade, so you can see water, ice at different levels, freezing and thawing. And the important part here is that you do at some point in the day, you see these interparticle pressures between about 5 and 10 centimeters become negative. That means the films of water are now unloading, lifting off their overburden load, and you can, at least in principle, begin to segregate the ice from the soil here. And that's good. And these pressures are these are 6 bars. These are 6 times atmospheric pressure. All you have to do to lift it is get it to be less than, to get it, less than 0. But these are really, really big. Now, so the point was, our concern is that you can't really count on melting any time in the last 4 million years because it's just been too cold. The planet's reoriented itself, and it's cold. So the question then is, even without melting, you're still squeezing ice into unfrozen water and back again. Even without melting, can you generate enough force to lift the grains? And the answer is yes, of course, or I wouldn't tell you. This is a case from only 30,000 years ago, and again, these are all being run for the Phoenix landing site, so we haven't looked at a lot of these things. The ice is much deeper in this particular case, and these are the interparticle pressures. This is about this greatest value here is 30 centimeters as opposed to 5 or 10. And the force is only about 1/10 what it was in the case of complete melting. But this still makes the nut in that you're able to at least lift off, begin the process of forming these ice lenses. And again, as I said, these things are pretty, these are the fundamental way in which terrestrial cycrophiles work, is that those thin films and their existence allows them to do everything they do. And it also seems to be producing this very interesting, segregated ice at Mars. Now, I'm going to finish up with just a little bit of a mention of where we're going from here. But first, we need to assess. I showed you those two pictures of the ice. One of them was segregated and it was nice and clear, and the other one was just dirt and ice intimately mixed, and it just looked like dirt. Well, they both happen right here, and nothing in the model that I've shown you so far can tell you why you see one type of ice a meter away from a totally different type of ice. So what we have here is a little topographic map of the workspace, the ground in front of us, before we started messing it up. And the little robot arm pivot was right here. And over the course of about 90 days, we just tore the heck out of this. But this is what it looked like before we got started. That way is north, and that means that these slopes here, and I've overlaid the sites of the two trenches here. This slope here, particularly the one, Dodo, which had that really nice segregated ice, is a south-facing slope. And we're at 70 degrees latitude. That's getting a lot warmer than the Snow White Trench, where we had basically gone sort of over the crest of a tiny hillock, but it did not have a north-south slope to it at all. This is a really warm site. Another thing that actually matters, this is the very first scoop of Dodo Goldilocks, and this is the first one from Snow White. And the other thing you notice here is the abundance of rocks up here. This is all totally fine-grained fluff down here. And that's also important because rocks conduct very well compared to soil. And so these rocks actually serve as heat pipes in order to sort of get warm temperatures down to that ice. And it's the key thing, I think, that we'll end up finding here is that the way to get the segregated ice is to find out, incrementally fine and small ways of punching up the temperature, the extra 5 Kelvin or 5 centigrade that you need to thicken up these ice lenses. But we will find out about that. As I said, the growth of a macroscopic lens depends on, can you run water from down here up through this frozen fringe to the ice and have it freeze there. And that's a serious, programming problem, and it depends on a number of things, including issues such as whether or not we really trust the soil parameters that we've got pulled from our libraries. There's some other things that we're kind of beginning to fold into this here. One of them is, just what I pointed out before. Can we explain the distribution of the ice that's in these trenches with this hypothesis? Is there something evident, and does it predict what we see, or does it predict something that you cannot see? What are the effects of the small rocks and landscapes? Also, what are the effects of salts? This soil is really salty. It's really salty. And more to the point, it has, some of the salts are deliquescent, meaning that above a certain relative humidity, they will just suck water out of the atmosphere until they become a puddle. Perchlorate is a notorious phase for this. And there's a paper just published, I don't even know it's out yet, is it? Selby's paper. I don't know if it's out, but a spectroscopic paper where they went back and they found little flakes about that size spectroscopically that look like discrete chunks of perchlorate in here. And so the hypothesis of these authors is that perchlorate is actually playing a role in getting bulk liquid to flow. So we may have to incorporate something like that and try to figure out, is this something they can do with a pure, clean water that bugs would like, or do you have to come up with some elaborate and strange chemistry that will make my head hurt? We're hoping not to do that, but it may turn out to be that way. Another sort of thing that came up is this whole other question: are we working too hard at this? There's a paper just published here in the last week or so where people have identified pattern ground in the vicinity around the Phoenix site. And these are patterns of rocks sitting on the surface. Here's an example from Heimdall crater, the one that we came in over. These are rock stripes on a steep slope. This is a different site where you actually get patterns of rock rings converting themselves into stripes on the slope. This is a diagnostic thing that terrestrial permafrost geologists have known for a long time. You get these self-organizing patterns of sewn stripes and sorted stone circles by a self-sorting process that derives from freeze-thaw. And so these guys are actually advocating that what you're seeing here is not evidence of these stupid little thin films that we've been worrying about trying to eke out of this, that you actually melted everything. It got really warm and really wet. It's not something that's easy to predict in the models that we have, but they have evidence, and so we're trying to evaluate. Maybe we've just made this harder than it needs to be. And then finally, the last thing that we want to do here sometime in the future is to do ask a little what-if question. If you had terrestrial psychrophiles, these microbes that live in cold temperatures, and they, the warmer it gets, the closer it gets to their ideal temperature, the faster they make babies, and the happier they are, and the more they reproduce. As you get lower and lower in temperature, their metabolic rate drops. As the population gets big relative to the resources, it drops to a very, very low level. And so they're kind of three different gears that microbes have in these environments. There's the growth level, where it's an empty playing field and all you got to do is make babies. A maintenance level of metabolism, where you're just maintaining. And then there's this sort of survival level. And as you can see, as you go colder going that way, it goes down and down and down. You're not doing very much anymore. In fact, it looks like basically in this sort of survival mode where the resources are extremely limited, what these organisms do is simply repair genetic damage due to protein racemization, things like that. Now, interestingly, this little rate actually looks just like some rates that you get for DNA change, but you cannot, at that level, keep up with things like radioactivity, galactic cosmic rays. Those things eventually add up and kill you. So we're interested in doing a little, time marching exercise to see if you put some in, if you inoculate this permafrost with some hypothetical population, and you let the planet wobble back and forth, you let stars explode and radioactive elements decay, and it gets warm and it gets cold. Is there any way to actually survive? Because when it's warm, you're reproducing like crazy, and when it gets less good, you tend to enter this long attrition phase. So balancing those things off would be interesting. Anyway, that's some of the sort of interfacial science-related stuff. It's going to be a while before you see any of it in publication, because it's all just, we're working it now. and which is why it's kind of a grab bag. But it did all have to do with, I think, some pretty exciting stuff that people are starting to realize about just how powerful these really, really small layers of unfrozen water can be. So thanks.
The frozen ground that was forming the polygons, how does that involve lots of liquid water? How did they come up with that?
The polygons don't involve liquid water. The polygons come from taking a mix of ice and dirt and cooling it really fast. What happens is the ice contracts, but because the ice is everywhere, it can't shrink. So what it actually does is it cracks. It loses volume by forming these big polygonal cracks to relieve the stress of trying to contract in every direction at once. You don't do that with pure ice, and you don't do it with just frozen dirt. It's got to be ice and dirt together.
About soil, rocks, and dirt rather generically,
Yes.
because it seems to me that would have a strong influence on much of your data as to the composition of the soil, as to where ice crystals and water transposed and so forth. Why did you choose the particular two soils that you selected? And are they indicative of the site where you did this work in Antarctica? And why didn't you analyze the soil to begin with?
Which soil? The soil in Mars?
Antarctica.
Oh, we did. We did.
So what was the composition, and how did that affect your results?
Well, we only had the soils that were there. And those soils were mostly glacial tills with some pyroclastic stuff and a little bit of weathered old volcanics.
I mean, chemically.
Mineralogically, or?
Elements, what are they?
Same thing that's in most rocks. There's silicon and there's oxygen, there's magnesium and calcium. Basically all of the ions that I showed in that chart, potassium, and then the anions that we had are all derived from the atmosphere. The chlorine, the sulfate, the nitrates. Those things all come in from the atmosphere. They're not part of the original soil. But it depends on a lot of things. This interaction. It depends on the chemicals there. It depends on the crystal form they're in. Depends on the physical processing that the soil gets, how big the grains are, whether there are lots of little concave surfaces on them or not. It's sensitive to a lot of those things, and there's a big library of these things, and the one that we chose in particular for this is a silt that looked just like looked very similar to the extent that we can analyze it, the soil that we saw at Phoenix. So we grabbed it, because we know silt is the best soil there is for making segregated ice, and B, because Phoenix had a silty soil.
Can you say anything about the nitrogen that you detected at the University Valley site? And I know nitrogens weren't detected at the Phoenix site, and I had heard that the challenge there was the perchlorate was very responsive to the sensor. So
because we didn't use the same. We did not.
it wasn't the identical instrument.
We didn't use the wiggle sensors. Those were sent to the lab. Yeah, and I probably have a list of the nitrate phases that we found, but I can't recall off the top of my head what they were. But yeah, nothing at Phoenix, of course. The missing nitrogen.
Okay, Aaron, we have a special gift, memento.
Thanks, thank you.
Talk today. And if you'll join me in thanking Aaron for his great talk.
Thanks.